Hello, this is the electromagnetic spectrum. Bum, bum, bum. So this is probably one of the cooler parts of astronomy. First off, as I'm probably going to mention this a lot, the only reason why we know anything about anything out in space is because of light. And when I say light, I don't just mean visible light. I'm talking about the entire electromagnetic spectrum, which we're going to learn about in this video. But up until 1800, for all of human history before that, all we knew about was visible light, was the light that our eyes could detect. But our eyes are only so good at detecting electromagnetic radiation. They can only detect a small, tiny piece of the actual radiation in existence. So along comes William Herschel. First off, scientists had been playing with prisms and bending light for years. Newton actually did a lot of groundbreaking work with this. He's famous for his physics, laws of physics, and also for inventing calculus. But he played with light a lot too. So that wasn't new, and that was a couple hundred years or so before. But William Herschel, our fellow astronomer who discovered Uranus back last semester, we talked about that. He liked looking at light in space, and in particular also light from the sun. And light from the sun, when it goes through a prism, bends into different colors. So he had a simple thought. When you think about it, it's like, oh, why didn't they think of this earlier? He thought, I wonder if the different colors here will basically be at different temperatures. If I stick a thermometer in front of here, any of you who've tried to fake a fever and be able to stay home sick, you might have stuck a thermometer in front of a light and know that light bulbs give off heat. And same with the sun. The sun gives off heat. So it's not a large stretch of the imagination to stick a thermometer in front of these colors of light and see if they treat see if these different colors of light basically give off different temperatures. So he did that. He's like, oh, cool. Blue is this temperature. Yellow is this temperature. Red's pretty warm. Well, let's just for the heck of it, let's just stick it out here and see what's going on. What? It's actually even hotter out here. The temperature's even higher here than it is over in the visible part. That means that light, there must be something coming from the sun over here that the eye can't see. Oh my god! And since it's right next to red, but not able to be seen, why not call it infrared? So to me, that's just so cool that testing, and it wasn't even expected. It's not like, oh, I wonder, maybe it was, who knows, but very well could have been, I wonder, what's going on with the light here, accidentally discovering invisible light. I don't know, that's pretty cool to me. And so that was 214 years ago that this was discovered. And I'm sure he was probably like, well, if there's something over here, must be something over here too, right? But the thermometer method doesn't really work so well over here. So that was kind of a dead end for William Herschel. But a year later or so, this guy, Johann Wilhelm Ritter, heard about this and was like, oh, that's pretty cool. I'm gonna see if I can find anything over here. I'm gonna take a stab at it. And so he tried a bunch of different things. And also, sort of coincidentally at that time, photography was just starting to be developed. I looked on Wikipedia, and I think the first surviving photograph was created in 1826 or 27 by Josef Nick. I don't know. This is the Wikipedia page I'm on, history of photography. But definitely it looks like around, for as much as you can trust Wikipedia, I don't see any issues here. Looks around 1800 that attempts were starting to be made with materials such as silver nitrate, and also silver chloride, which is what I guess Ritter was using. And so Ritter realized, well, I know that if you shine light on silver chloride, it will make a chemical reaction. The silver chloride will change. In fact, let me show you a YouTube video of that working before I keep explaining. Take a listen at this.
Well, we can also use this energy, this light energy, to bring about chemical reactions. And this is, of course, the basis of photography. Now, we have here a plate. We've made this with some jelly and some silver chloride. And at the moment, this is a nice white colour. Now, we're going to put a mask over this and shine some light on it. Okay. So, we have the white silver chloride. We're shining the light onto this now, and the light is causing a chemical reaction. The light breaks down the silver chloride and forms some silver particles. Now, these are a very different colour from the silver chloride. The silver chloride is white. The silver itself, well, silver is a metal and slightly metallic coloured. We should be able to see some of the silver being formed in this reaction. So we just need to give it a decent amount of time in order for it to react. So let's try this. Okay. And if we hold this up, you should be able to see here, there we are, silver chloride going to silver. And this reaction is brought about by the light energy. Okay, what else can we do with light? Well,
So that's cool. So Ritter was like, all right, well, I have these strips of silver chloride, and I know if I shine bright light on them, that they will basically have that reaction you just saw in the video. I wonder if the reaction will be different at the different colors of light. And also, because I'm really looking for this magical light over here, invisible light over here, I wonder if that'll work. So he took strips of silver chloride and definitely noticed that the wavelength of light, or the color of light, made a difference. And that when he stuck a strip of silver chloride over here, whoa, it was the most reactive of them all. Dang. And so, at least I think that's what I read. But anyway, there was light over here that the eye couldn't see that caused a reaction, a chemical reaction to the silver chloride. So, bam, and within the span of about a year or so, whole new parts of the spectrum, which it didn't even, people didn't even realize that it existed, were discovered. And that's really cool. So then, well, if something exists over here and over here, then it's not too far a stretch of the imagination to think, okay, keep going, out to infinity, keep going this way, out to infinity. And currently, 200 and something years later, we know that this definitely exists. Actually, it wasn't too much longer after this discovery, well, I guess less than a century, that it was scientifically proven with equations and all that stuff derived, that this relationship exists. So, and it was called the electromagnetic spectrum. Electromagnetic because of the following. It's come to realize that light travels as a wave, and this wave has both an electric aspect to it, which you can see is this darker red, and you can see the E. This is the amplitude of the E wave, and it also has a magnetic aspect to it, which I don't know if you can tell, but this magnetic part, and here's the amplitude of the magnetic wave, is perpendicular or 90 degrees to the electric one, and they're out of phase. Again, it's hard to tell. This peak for the magnetic actually is like would be right in between the two peaks for electric, so they oscillate back and forth. And what I find amazing about this is, unlike ocean waves that, if you throw a rock in the water, the ripples kind of get weaker and weaker as the energy dissipates. These waves don't get weaker and weaker. A light wave can travel essentially through space all across the universe. We get light from galaxies that are essentially across the universe, that had left those stars and galaxies billions of years ago, and reaches us. Wow. So this can travel forever in a vacuum, which is pretty cool. But it also acts like a particle, which we call a photon. You might have heard before, a photon of light. That just doesn't mean photon of visible light. As you can see here, visible light is just a tiny portion of the entire spectrum. This range is deceiving. It looks like visible takes up a bigger part of the spectrum, but it's really much thinner. But yeah, it was also noticed that if you shine light on a metal like, say, potassium, that if the light high enough energy, electrons can be ejected off, which sounds like a particle, right? You throw a baseball at some water, and the water splashes up. You throw the baseball harder, water splashes up higher and moves out faster. So, strangely enough, light behaves like a particle and a wave, sort of at the same time, or what's cool to notice about this is it's red light seems to have less energy than purple light. In fact, as you go at higher wavelengths, at shorter wavelengths, which is also the Roy G. Biv colors, you go from red to purple, and violet, the energy increases, the wavelength decreases, and so that's essentially the pattern for the electromagnetic spectrum. You got long wavelength, low energy here, short wavelength, high energy. So radio waves come from cold, low energy objects. Gamma rays come from hot, really hot, high energy objects. So, and that's really the difference. You get a photon of light. A photon of visible light is identical to a photon of radio, which is identical to a photon of X-ray. All those are identical. The only difference is the amount of energy contained in it, which then affects the wavelength of it. So we're going to go through all of these. I think I can fit in radio only in this video, and then next video I'll start with microwaves. But I'm going to try to show you a picture of the sun at each of these different groupings or parts of the spectrum, and also some other fun things. So for radio, this is what I found. First off, this is an article, so I'm going to scroll down, and you can just pause. I'm going to scroll down kind of quickly, and you can pause the video if you want to read it. You don't have to necessarily read this, but it's pretty interesting. This picture though is cool. If you want to get, because you know that you can use a telescope to see stars and things far away in space, but that's visible light only. The telescope only works in, that you might buy it and have at home, only works in the visible part of the spectrum. When I say telescope, I mean a visible light telescope that you would buy if, like a hobbyist or whatever. But you can use telescopes for all of these wavelengths. In order to have a telescope work for radio, which has such long wavelengths, you need big radio. You need big dishes, big telescopes. You can either have one really big dish, which you soon find out is not enough if you want to go really far away and get some high resolution. So then instead of building a huge dish that's like kilometers in diameter, like, can you imagine trying to build one big dish that's 36 kilometers across? Not going to happen. But what you can do is sort of cheat in a sense, not really cheating, but it's, is you can build a bunch of smaller ones, which are still pretty big, 25 meters in diameter, and then spread them out over 36 kilometers, and you essentially get the same effect. Alright, so let's scroll down so you can read this. You can pause this video and read it. Okay, I'm going to go down and alright, you can pause and read now. Here's another picture of the electromagnetic spectrum and examples of how big the wavelengths are. Radio wavelengths can be as tall as buildings or as short as humans. Microwaves can be like, they're sort of biggish but insect size, etc., etc. Alright, actually, yeah, so pause and read there, and pause and read there, and okay, pause and read here. But actually, this is a cool picture. If our eyeballs were not suited for visible light but instead for radio light, this is what we would see. It's pretty cool. And stop and read. Alright, so this is a picture of our sun in the radio wavelengths. It looks as though the sun gives off light in the radio wavelengths throughout the entire, diameter of the sun, but the peak of radio waves are given off in these areas here, and there are two bands here. When we talk about the sun, we'll talk about what's going on with these two bands. But that's a pretty interesting thing to notice. If you look at the sun in visible light, you wouldn't see this feature necessarily. You might see hints of it with sunspots, but yeah, that's the cool thing about looking at objects at the different wavelengths. They show hidden features that visible light doesn't necessarily show. Things that were hidden to humans before the 1800s. Okay, stop and read. Alright, I'm going to stop the video here, and then next video we'll go on with microwaves. Bye-bye.